So we're told we have a mechanism. So these aren't what we might think of a normal chemical equation. They're elementary steps. Now first let's write the overall chemical equation. I'm going to just write these elementary steps right here. So anything that occurs on either side of the chemical arrow, it's like simplifying equations in algebra class. I'm going to say that D cancels out, and I'm going to say there's two B's, so I'm going to put a coefficient of 2 there, and I have C and X. So that is the overall equation right there. So when we go into the lab or look at reaction and come up with a chemical reaction, this is what we get. We get the products and reactants with no clue of how it happened. But when we measure kinetics, we can get a picture, and then we can use elementary steps which tell us what's happening. So identify any intermediates. What do you think? Yeah, it's going to be D. Now when we write the rate law, it's based on the slow step, and these, we can look at them and use them to write a rate equation, unlike a chemical equation. An elementary step gives us the molecularity, and so the rate is going to be equal to some rate constant. I see this chemical species A, and I see a chemical species B, and that is it. So once again, there's no way to look at this and say what the rate law is, because it's just a chemical equation. These are elementary steps, and we can look at looks just like a chemical equation, doesn't it? That's half the confusion. We look at the slow step and say that gives us the molecularity. That tells us A and B have to come together, and so it's going to be first order with each of those, and it's a second order overall reaction. K would have those second order rate constant units. What is the definition of a catalyst? Something that allows a reaction to occur. We typically say it speeds up a reaction, but we say it remains unchanged in the chemical reaction. But in terms of the Arrhenius equation, it lowers activation energy, and so that speeds up the rate. And this looks real similar to what you did with hydrogen peroxide and potassium iodide. So catalyst can do two things. It can lower the activation energy, or it can change this orientation factor, this thing here, which said how many collisions have the right orientation for a reaction to occur. So there are certain things in nature that if we can hold something a certain way, a reaction will occur. Here's a common one chemists use in processing petroleum. It would be called catalytic hydrogenation. And so here is two carbon atoms, and there's a double bond between them. And here's hydrogen. If you just put these two together, they're both gases, under high pressure and heat them, maybe a reaction will occur. Now here is something like platinum or palladium metal, and the metal has orbitals that can overlap with the orbitals on the pi bond here, and the hydrogen comes down and overlaps with the orbitals and almost becomes free to move around, and then it can overlap with the orbitals on that pi bond, and here you see one hydrogen is added and then the other hydrogen adds, and now we have ethane. We went from ethene to ethane. Just a little bit of OChem for you there with those names. So we might think of this as an orientation factor. And nature's real good at this with enzymes. An enzyme is a protein that causes biological reactions to occur. And we like to think of a substrate being a molecule that a reaction is going to occur on. And it fits into this enzyme. So here's some molecule, and a protein has like a pocket or a shape, kind of like a lock and key analogy, and it fits in there. And sometimes I like to say it's like an anvil, holds it in there like an anvil, and there's like a hammer and can smash down, and everything's perfect for a reaction to occur. And here they're showing enzymes in beef liver. Occasionally do it with yeast and hydrogen peroxide. So an enzyme really holds things in the perfect spot, and that can cause, I think like a shop bench device holds it there, and you can
do whatever
is needed. Get a bigger hammer. So back by popular demand, more thermodynamics. That's what students love and enjoy. Good, I'm making somebody smile. So the first law of thermodynamics is energy is conserved, and we saw how that works with any changes that occur being heat or work being done on or by the system or surroundings. Now we consider that reactions have disorder and direction and free energy. So I like the idea of direction. Reactions, they go forward, or we might say they can back up. And shortly we're going to talk about equilibrium. So maybe that's why this chapter becomes before the equilibrium chapter. So let's look at some obvious pictures. On your left, what would be the before and after picture? Is this the before? This the after? No. You see that, you immediately think this is at one point in time, this is some point in time later. So we can there's the direction. And then the previous slide said something about disorder. What is more ordered? This is definitely a mess. It has less order than everything nicely contained there in those two eggs. So when this occurs spontaneously, what does that mean? Any process that occurs without outside intervention is said to be spontaneous. So granted, the guy had to loosen his grip on these eggs, but they spontaneously fell to the countertop, broke into pieces, created a mess. Process that is spontaneous in one direction is not spontaneous in the opposite direction. Now we can videotape it and run the film backwards, and it looks like it occurs. This is spontaneous. This is not spontaneous. Well, something that seems really super obvious might be this over here. Here we have a gas at 1 atmosphere. Here's an empty flask. It's a vacuum. There's nothing in here. And we open this stopcock, and what happens spontaneously?
Pressure equalizes.
Yeah, the pressure equalizes. Move it over there. So you can see we have 1 atmosphere. These flasks are about the same size. So now it's taking up double the volume. Pressure falls in half. This is probably a gas law. This process is spontaneous. If I said stand there and wait with the stopcock, when you see all the gas molecules move back in the original flask, cut it off and trap them. That'd be futile. So reversible and irreversible processes. A reversible process is one that can go back and forth between states along the same path. The system is restored to its original state. There is no net change in the system or the surroundings. So neither of those first two examples we looked at would be called reversible. What we just looked at is something that's irreversible. The dropping of the eggs, the gas being equalized in the two flasks. So what's a good example of a reversible process? Well, now we're going to throw in temperature. That's why there's thermodynamics in this chapter. Processes that are spontaneous at one temperature may be non-spontaneous at other temperatures. Above 0 degrees Celsius, it's spontaneous for ice to melt. Below 0 degrees, it's spontaneous for water to freeze, or we say the reverse process is spontaneous. I need to add more bolded points to this slide. When we're right at 0 degrees, that's our reversible setup. When we're right at 0 degrees, we can go back and forth from solid to ice. So this diagram looks just like the little gas analogy. An irreversible process can't be restored to the system and surroundings back to their original state. A different path with different heat and Q must be taken. So imagine this being just like those two flasks. We could say 1 atmosphere, pull this up, all of a sudden we have a half an atmosphere here. And we can't sit around and wait for the gas molecules decide to go in this half and then quickly slide this trap door in and trap the gas over here. But what we can do is push this plunger down, push them all back in here, and slide the door down. Now we're back to our original state, but a different path was taken. Probably when we pull this out, this thing cools, and most definitely when we push this thing in, this heats up. If you know anything about what's an air conditioner have on it? Yeah, a compressor. And so typically when a gas is compressed, it heats up, and then you run it through a little radiator outside and heats up the outside. Then when it comes back into your house, you let it expand through another little radiator thing and air blows through it. That's how your house gets cool. So if a process is spontaneous, it's also irreversible. It takes off in one direction without outside intervention. It's not going to go back the other way. For a system at equilibrium, notice 0 degrees is the equilibrium temperature for ice and water. So when we're at equilibrium, reactants and products are interconverted reversibly. For a spontaneous process, path between reactants and products is irreversible. So now we get to the second law of thermodynamics. And unlike the first law where you have a simple sentence, like 2 words, energy is conserved, and a simple equation, second law of thermodynamics, you have multiple sentences and kind of some multiple equations. It has to do with entropy. What is entropy? We give it symbol S. It was coined by Rudolph Clausius in the 19th century. He was convinced of the significance of the ratio of heat delivered and the temperature at which it is delivered, Q over T. Entropy is a thermodynamic term that reflects the disorder or randomness of a system. Your new edition of the book likes to avoid those terms and say entropy is the tendency for things to want to spread out and be in more states. So this looks like that first. You can say there's a vacuum here, there's no air. Here's 2 molecules. We could imagine they're gases. And we open this stopcock, and what happens?
Don't we not know? Says technique.
Yeah, I believe that. So let's do this. A little stopcock there. Let's just start with 1 gas molecule. I open up the valve. What's the probability that it's going to be on the H side? 50-50. It's like flipping a coin, right? That's why I use the H and T, heads and tails. Like Hayden said, we can't see, we don't know. So now, let me make it look like the PowerPoint slide. Now I got 2 in there. What is the probability that at some point in time, both of them are going to be on this side? 25%. Absolute. Did you take statistics? They go over probability and all those good things. You're right. 1/4 probability. And now this looks about like our slide here. And notice how many options do we have over here? If these 2, we open this up, we could have blue and red, we could have red and blue, we could have both on the right side, or we could have both on the left side. So notice this, there's 4. And I thought that was significant, because what is 1/4?
25%.
Yeah, so the probability. Alright, let's imagine this flask is big enough to put a mole of gas in there. How much is a mole? Now what's the probability? Let's see if you can blow up your calculator. Where's mine? Raise 0.5 to Avogadro's number. Avogadro number. Yeah, an avocado. What do you get when you cut a... Yeah, 0. Zero probability. Alright, well that was fun and interesting, I guess. So another thing I like to say about these gas molecules, they're not like when you and your sibling were in the back seat of the car. Did you ever draw a line and fight over, have those little things? Yeah. So gas molecules, they're this bouncing around. They don't know whether they bounce into the wall or bounce into each other, and they just randomly bounce around. Eventually, they bounce down this hole, and one gets over here. Now, my experience with gases, I like to think you open that valve and they blow and they push each other that way. But it's simply, it might go back to the way your book likes to describe entropy. Things like to spread out so they can take more states. And here's the number of states we could have with 2 flasks and 2 gas molecules. So it's probability statistics, why a gas expands to fill its container. So entropy is a state function, and when our change in entropy is positive, we say randomness increases. When delta S is less than 0, we say things have become more ordered, or we might say randomness decreases. So what I like about this equation, it's something you can comprehend, and it says suppose a system changes reversibly between state 1 and 2 at constant temperature, then the change in entropy is, and so I like to think about ice and water, and we're at 0 degrees. That's where ice and water are said to be in equilibrium with each other. But this is where you can go into the lab and get some numbers, and you'll see that entropy has the units joules per Kelvin. And now we actually get around to the second law of thermodynamics here. The change in entropy of the universe is the sum of the change in entropy of the system and the change in entropy of the surroundings. So previously we had system and surroundings, and that was it. We never talked about the universe. If we're at equilibrium, that's what the reversible process means here. We can have things changing, but regardless of the change in entropy of the universe is 0. It's for a reversible process. For an irreversible process, the change in entropy of the universe is positive. So if I was walking down the street and somebody said, "Hey, you, what is the second law of thermodynamics?" I'd say, well, any spontaneous change, you increase the entropy of the universe. And then they'd give me a $20 bill for enriching their knowledge.